our knowledge on our parent functions. Now, what we have gotten so far is we've gotten our absolute value function. That is the name of the parent function. And remember, that equation looks like a nice, pretty, taut, pointy V. And then we have our quadratic function. Our quadratic function is a nice, smooth U, okay? So we have to know the names of our functions and the equations of our functions, okay? This, and let's scoot this over just a little bit more, okay? This is a picture of what our parent function of our absolute value looks like. The equation for this is f of x equals the absolute value of x. We have seen this, we have done this, a nice pretty V. Our vertex is at 0, 0. These are not lines. This is an absolute value function. If we're going to talk about what happens to the function, we say the function shifted whatever direction or moved whatever direction. We don't say the lines. You can also say the vertex changed from 0, 0 to whatever our new vertex is. On this one, we also have an axis of symmetry. It goes straight down the middle. The axis of symmetry is the equation of a line. Whoops, let's back up the track here just a little bit. This right here is our quadratic function. This is what our parent function looks like. Our vertex is at 0, 0. The difference between our vertex on the quadratic and the vertex on the absolute value, the quadratic is smooth, okay? We have a smooth U-like, and the absolute value is a nice, pretty, pointed, taut V, okay? And again, if we're talking about this graph, we would not say lines. There's no lines here. A line is infinite. It goes on and on and on in one direction and the other. And it's straight. On a parabola or an absolute value, it's not a line. It is the graph of a function. Okay, a line is also a function, but a line is a line. The absolute value graph is the absolute value graph. The quadratic is called a parabola, but a parabola, this parabola that opens up or down, is specifically a quadratic function. You may want to put that in your notes. The graph of a quadratic is called a parabola, okay, and it is a function. Okay, we've had these, we've seen these, okay? This is the absolute value function in vertex form. So when A and H and K, when we have numerical representations here, we can determine vertical stretches. Did my Y values, my function values get larger, or did my Y values, my function values get smaller, okay? So we're talking about a compress, and a compress may appear that the graph itself gets slimmer or smaller, but we're not talking about the graph appearance. We're talking about the function output, okay? So A determines my vertical stretch or shrink. We're using expansion and compression. My H represents my horizontal shift, shift left or shift right. My K represents my vertical shift. Notice the sign and the variable are the same color. That means whatever this is, if it's a +1, then my absolute value shifted up 1 unit. If it's -1, then my absolute value shifted down 1. Notice that this is already a minus. H is simply on its own. Therefore, to have x plus h, so if we saw something like the absolute value of x plus 3, and we're determining the horizontal shift, in order for it to be a +3, because our vertex form is a minus h, then h would have to be negative, and I can show it would be x minus a -3. We don't see that. We know minus a negative, we know this becomes positive. So they're not going to show us this. They're going to show us this, and we have to know to determine that horizontal shift in order to see a +3, that h value is a -3. And same goes for if we see x minus 5, it's already minus, so 5 would be my horizontal shift, okay? We need to keep that in mind. Be sure and put that in your notes any way, shape, or form that it brings your attention to that so you remember. X equals H, my H value is the axis of symmetry because it goes right down the middle. The axis of symmetry says if I fold my graph, regardless of what it is, if I fold my graph along that axis of symmetry, every point on the left matches up with every point on the right, or every point up at the top matches every point at the bottom. Doesn't really matter. An axis of symmetry means I fold it along that line, every point will match, okay? We also, and notice this is color-coded. Now this is our quadratic, okay? Notice what's really cool. We still have the same colors, and you might say, okay, why? Why? Because here's the deal. My leading coefficient, my A, still is going to represent my expansion, my stretch, or my compression, my shrink, okay? HK is still going to be my vertex. X equals H is still my axis of symmetry. Each time, every time, all the time. So if we know one of them, we know it all, okay? Now, just really quickly, before I go on, I'm going to pull up my Desmos, okay? And we're going to talk real quick about what, now, we don't always graph them. We need to be able to quick and simple recognize, is this going to be a stretch? Is this going to be a shrink? And I'm going to show you. If I use an A value that's greater than 1, any value that's greater than 1, because in my parent function, my A value is 1. So if I use any value greater than 1, so let's just use 2. 2 times the absolute value of X, okay? If I compare that to my parent function, by appearances, it may look like my graph gets smaller. But if you will notice, my Y values, my output gets larger faster. I'm expanding. So at 2 on my parent function, I'm at 2. But at 2 on the new function or the transformed function, my output value is 4. Can't seem to get right on that, but it is 4 right there. Okay, my output value is 4. So you can see my Y values are getting larger faster. They're expanding. This also happens, okay, for my quadratic. Yeah, let's go. Okay, there's my parent quadratic. If I give that quadratic a leading coefficient, and we'll just stick with 2, and it doesn't matter, as long as it's greater than 1, okay? Look, my Y values now, again, the graph may appear as in visually that it's smaller, but we're not talking about a visual appearance. We're talking about a vertical expansion. Vertical means my output values. My output values of my red graph, which is my transformed graph, are larger than the output values of my parent graph. So on my transformed graph, my red graph, my new one, the one that has a coefficient of 2, my output value was a 4, okay? So get it right there, I can't see it very well. Or at 1, I'm sorry. At 1, it was 2, okay? So, but at 1 over here on my original one, I'm at 1. It's a 1, 1. So my output values got larger. It expanded. My output values expanded. So let's turn the expansion off. And remember I said had to be greater than 1. So it only makes sense if we're less than 1 that it is a compression. My Y values, my function values are getting smaller. So if it was greater than 1, it's larger or expanded, so less than 1, okay, and I'm just going to use 1/2, okay, as long as it's less than 1, okay, then I have my X squared, okay, and again, it looks like it's wider, but I'm not doing appearances, I'm doing function output values, okay, so my output value at 2 was a -2, I'm sorry, my output value at a -2 was 2 on my transformed graph, but on my original graph, my output value at 2 was 4. Everybody there, okay? So it is important. Now, I need to specify. I said less than 1, but somebody could say, okay, a -1 is less than 1. But let's see what happens when I just use a -1. okay? I'm just gonna put a negative because the one's understood. It reflected. We are not doing reflections right now. We are not doing reflections right now, okay? So what we're doing is vertical expansions or compressions. And remember, I told you if we learn one of them, we learn them all. So we've already said that if A is greater than 1, we have a vertical expansion or stretch. We're using the words expansion and compression right now, but they go hand in hand, okay? But I already showed you what a negative looked like, so technically, if A is between 0 and 1, it's between 0 and 1, it is a positive number, then we have a vertical compression or a shrink. Now again, it may appear, okay, it may appear that my graph got larger. I'm not looking at the appearance of the graph. I'm considering the output of the graph. My output of this graph is smaller than the output of this graph. Each time, every time, all the time, if my leading coefficient, my A value is between 0 and 1. It will work on every single parent function we get. You know how it works with one of them, you know how it works with all of them, okay? So I'm gonna jump back over here, maybe, if it lets me, okay? So we've had these, we've done these. Now here's the thing, okay? We're getting a new parent function, okay? We have the absolute value function, f of x equals x. We have the quadratic function, f of x equals x squared. And now we're getting our cubic function, f of x equals x cubed. Now, my absolute value is a nice, pretty taut v. Now, eventually we will do reflections, so any v, each time, every time, all the time, wherever we see it, if it opens up or down, if it's way over to the left, way over to the right, it doesn't matter, it belongs to the absolute value function. On a quadratic, we have a nice, smooth u, and I probably should be putting these little arrows on it because we don't stop, they continue, they go on and on, okay? So each time, every time, all the time, we see a nice smooth U, whether it opens up or down, it's over way to the left or way to the right, it's not relevant. It is a parabola, it is a quadratic function, okay? And now our new one is a cubic function. Cubic means I have a cubed right here. This is my parent function, this is the name of my parent function. Now, this one, and I'm not an artist, so, okay, is like an S, okay, and I curve that, and it's not really curved, okay, it goes like this, there we go, something like this, okay? So, again, every single time that we have this, it is going to be a cubic function. We're gonna look at what the parent cubic function looks like. My parent cubic function is like that. Again, and it's not necessarily a vertex, I call it a turning point, okay? You can call it a vertex, you can call it a turning point, either one. I guess you could call it a vertex because it turns, okay? Is at 0, 0, okay? Just like our absolute value function, our vertex of our parent function was at 0, 0. The vertex of the parent function of our quadratic is at 0, 0. So it only makes sense that our turning point, or our vertex, so to speak, on our cubic function is 0, 0, okay? Now, again, the beautiful part, our cubic function, okay? F of x equals A, the number up front, the leading coefficient, represents my vertical stretch or shrink, my convention or compression. My horizontal shift is represented by h. My vertical shift is represented by my k, it's tacked on the back. HK is the vertex, or you could say the turning point. I didn't spell that right. Or the turning point. Or the turning point, okay? And keep in mind the equation is f of x equals x minus h cubed plus k. Therefore, to have x plus h, same thing. H would have to be negative, all right? Let's put this right here. And let's just, we'll do a couple of them. F of x, I don't know, equals 1/2 x cubed, okay? Well, A is between 0 and 1. This is A 1/2. Nothing is grouped with h. H is my horizontal shift, okay? Nothing is grouped there. The mathematical value of nothing is 0, okay? What's tacked on the back? Added or subtracted back here. Again, there's nothing. The mathematical value of nothing is 0. K equals 0. So if we're going to talk about the transformations, okay, my turning point or my vertex, so to speak, is 0, 0. That did not change from my parent function. What did change is my output values. And since A is between 0 and 1, it is less than 1, then I have a vertical, that means my output, I have a vertical compression because my output values got smaller by a factor of 1/2. Okay? Now, if we wanted to make that a little bit, let's see, can I scroll down a little? I'm not sure if I can. Oh, we'll just add another one. If I wanted to make that a little, twist it up a little bit, I'm still doing a cubic function, f of x equals 3 times x plus 4 cubed, because it's a cubic, minus 2. Let's do plus 2, okay? And again, I'm comparing this to my parent function. And remember, my parent function looks like this, okay? And this point right here is a 0, 0, okay? Well, here's the thing. First thing I see is I have my 3. That 3 is my A value. So A is 3, which is greater than 1. So I have an expansion. And it is a vertical expansion because of where this is located. We have a vertical expansion. And that expansion is by a factor of 3. My H value, since that is x plus 4 and it's supposed to be x minus, then H would have to be a negative 4. So my H value is a negative 4. I'm not sure where that little dot came from. Okay? Then I have my K value. My K is tacked on the back. My K value is a positive 2. So my turning point or my vertex, and I'm going to also put turning point because it turns there and goes down. My turning point from my parent function, it changed from 0, 0 to my H value, negative 4, comma, K value is 2. And I have a vertical expansion. I got larger, output got larger. I have a vertical expansion by a factor of 3. Oh, a vertical expansion, yeah, by a factor of 3. Sorry about that. By a factor of 3. Okay. Now, what I'm going to do is I'm going to take that exact one and we're going to play with it over on Desmos just for a couple of minutes. If I come over here to Desmos, let's find it. Okay. Let's get my writing off of here. Okay. All right. I'm going to turn these off. I'm going to quickly do. And this is just a visual. We don't want to have to take the time to graph all of these if all we're doing is identifying the transformations. This is the parent function. This is what it looks like. Now, if I want a vertical expansion with no shift or anything, an expansion, I would have to have a number greater than 1. So I'm going to go ahead and do a 3. Do you see how I expanded my Y values, got larger, faster? That is my, and let's see if I can zoom in a little bit. Okay, over here. So, and let's do this a red real quick. So maybe it's a little bit easier to see. A red, okay. So, my transformation is in red. That is the 3. Okay, now if I want to do a horizontal shift, and I'm going to do this as we go, okay, we had a negative 4 in between, grouped with that x. X minus a negative would be x plus 4. Do you see how now I had a shift left because it was a negative 4, okay? And I'm sorry, I do not remember what I tacked on the back. I think it was a plus 2. So we're going to hit plus 2. And the plus 2 gives me my vertical. It goes together. It's exactly how it appears. So I'm going to do a plus 2. And now my turning point went from 0, 0 to a -4, positive 2. Okay? So let's look what a compression would look like. Let me go ahead and put all of this back as if we're just messing with that so you can see the comparisons. Okay? And I'm going to make one smaller. I'm going to make it shrink. So in order to shrink, I need between 0 and 1. If I'm between 0 and 1, let's do maybe a fourth. Okay? Let's do 1/4. And look how and we need another color. Sorry about that. We'll go blue. Okay. And look how my Y values, my output values got smaller. My output values are smaller, okay? So between 0 and 1, I have a vertical compression, a vertical shrink, okay? So let's go back to here. All right. One thing I need to bring to your attention. Notice on my cubic function, okay, vertex or turning point, I can do that. I don't see where it says anything about the axis of symmetry going down the middle. Let's see. This had an axis of symmetry, and it was exactly the same as my absolute value. Well, okay. If I have an axis of symmetry, that means I can fold my line along, I can fold my graph along my axis of symmetry. Well, the axis of symmetry here, we don't have one. I can't fold it along here or even along here. I can't fold it along the x-axis or the y-axis so that every point on the left matches up with every point on the right. If I tried folding it along here, okay, if I even if it was y equals a -x or y equals x, a diagonal, every point up here isn't going to match every point down here. So we need to know that an axis of symmetry on a cubic function, we don't have one. It doesn't exist. So you need to take this information and be sure it is written into your journals so that you will have access to it if and when you need it again or when you're reviewing for a test.